Everyone, so we're looking at this Unit 9 in class review, and you're either, actually this is extra if anyone's interested in Unit 9. So enthalpy is the delta H, it's the change in energy. Reminder that if it's endothermic, that'd be a positive delta H. And a negative delta H would be exothermic. Entropy, though, is our delta S. This is our measure of chaos. So if we have a positive delta S, it's more chaotic. Oh my goodness, how do you spell chaos? Let's do ordered. It's less ordered. And then a negative delta S is more ordered or less chaotic. Now, if we are saying that something is, like a reaction is driven by something, it's either driven by the enthalpy or the entropy. So the negative delta H, this would be a driver of a reaction. This would be pushing a reaction to have a negative delta G, which is thermodynamically favorable. Or the driver could be a positive delta S. So if you have a negative delta H, that would be the driver. If you have a positive delta S, then that's what would be driving a reaction to make it thermodynamically favorable, which means that we have a negative delta G. That Gibbs free energy is negative, and when that's occurring, the reaction is happening. Okay, I wasn't sure if we'd have a couple other vocabs, but I didn't run into any that I was worried about, so let's keep going. Now, on your blue reference, let's see if I can find where this is at. Right here. It says delta G is equal to delta H minus T delta S, okay? So delta G is equal to delta H minus T delta S. Now reminder, when delta G is negative, this is thermodynamically favorable. This is a good thing. And like I was telling you, when delta H is a negative number, this is pushing delta G to be negative, so this would be the driver. And then notice we have this minus sign, and if you minus from a positive number, then that would cause this to be negative. So the best case scenario is when delta H is negative and delta S is positive. Then at all temperatures, delta G will be negative. This is thermodynamically favorable. Whenever delta G is negative, that means that our K is going to be larger than 1. And if this is a cell, like a galvanic cell, a battery, or a voltaic cell, that would give you a positive voltage. Now, the exact opposite of this, though, when delta H is positive and delta S is negative, then it doesn't matter the temperature. At all temperatures, where you're going to have a positive delta G, which means this reaction is not happening, our K value is going to be larger than 0 but less than 1. And then you might calculate a negative for your voltage, but it would actually just be 0. Okay? And so if you get a negative, it's not actually negative, it just would have 0 voltage. So now we get into these two situations where there's a driver. For example, when delta H is positive and delta S is positive, that's when delta S is the driver. It's what's trying to cause the reaction to be, or delta G to be negative. So like sometimes delta G is positive and sometimes it's negative. And here's those scenarios. So positive means at high temps the reaction does happen, that it's a negative delta G. But if it's positive, positive, and it's low temperatures, then delta G is positive, the reaction's not happening. And then we see this mimicked here. We know that whenever delta G is positive, our K value is greater than 0 but less than 1. And that's when we might calculate a negative voltage, but actually it's not negative, it's 0. When it's a negative delta G, that's when our K value is greater than 1. And we'd have some positive number for our voltage. Now when they're both negative, this is when delta H is our driver. So sometimes it's going to be positive and sometimes it's going to be negative. So like sometimes delta G could be positive, sometimes it can be negative. And it is going to depend on the temperature. So negative, negative, low temp gives us a negative delta G, but negative, negative, when you have a high temp, then the reaction does not happen. That would be a positive delta G. And then we're consistent with before, whenever the delta G is positive, K is in between 0 and 1. When it's negative, then our K value is larger than 1. And this is when you might calculate that it's negative, but it's not. It's a voltage of 0. This would be some kind of positive voltage. Okay, now I wanted you to recognize like delta H, delta G, and K values. So I have 3 reactions here. I have delta G's, delta H's, and K values for each of them. And we're going to try to get to this overall reaction. So see how there's 4NH3 on the reactant side? Well, here's 4NH3 on the reactant side. So I could take this reaction and I would just leave my delta G the same. I wouldn't change that. The delta H I wouldn't change, and my K value I wouldn't change. Now notice we have 8O2. There's a lot of oxygens going on here, so how about we save that for last? Now there's 4 HNO3s on the product side. Well, right here I see 4 HNO3 on the product side. So how about I take this third reaction and I leave it just the way it is. So that would be 4NO squared plus O2, O plus 2 waters. That's going to give us 4HNO3. And again, because I didn't flip this reaction, because I didn't multiply this reaction, this will just mean that the G value, the H value, and the K value all stay the same. Now the last thing I'm seeing here is 4 H2Os. Okay? Now 4 H2Os are actually okay right now, because see how we have 6 H2O and 2 H2O? 6 of these will cancel with 2 of those, leaving us with 4 H2O. So what do we need to add to get to this final reaction then? Because I see 5 O2s plus 1 more, this would be 6 O2s, but it's saying I need 8 O2s. The other thing I'm noticing is there's no NO in this reaction. But I have 4 of them right here. So what if I take this second one and I flip it so that way the NOs can cancel, but then I also double this. So let's start by flipping this reaction. We have NO2 plus O2 turns into NO2. Now this guy had a coefficient of 2, but I'm going to double it. This one had a coefficient of 2, but I'm going to double it. This had a coefficient of 1, but I'm going to double that. Now we did 2 things. We doubled the reaction and we flipped it. So delta G's are the same as delta H's. That if you flip a reaction, you'd make it negative. so negative delta G2. And because we doubled the reaction, we would double the delta G. So then, same thing here, because we flipped the reaction, we do a negative delta H. Because we doubled it, we'll multiply it by 2. And then finally, K values are weird. Because we flipped the reaction, we're going to do 1 over K2. And because we doubled it, we raise it, the K value, to whatever the multiplier was. So let's see what this gives us overall. So here, I'm seeing 4 NO2s, 4 NO2s. Oh, what did I write down wrong here? Sorry. This is reaction 3, okay. 2s. Sorry, this is supposed to not have a subscript of 2 right there. Yeah. And then this means that this 4NO can cancel with that 4NO. And that would leave us with 4NH3 plus 5, 6, 7, 8 O2s. And that will turn into 4 HNO3 and 4 water molecules. Right there. Great. So we do have this overall, which is wonderful. Now, how do we get the delta G for this fourth reaction? Well, to get delta G of this fourth reaction, we would take delta G1 plus delta G2 plus this negative delta G, sorry, this is delta G3, delta G2 that we also multiply by 2. So it'd be negative 1, 0, 1, 1. And then the third reaction, so plus negative 1, 6, 6. And then this was 71. And so we'll double it because we doubled the reaction. But then it's a positive and we're going to make it a negative. So it'll be plus the negative 142. And so that would mean delta G would be negative 1011 minus 166 minus 142, negative 1319. Okay, nice. So there's our delta G. Delta H, we're going to treat really similar. I don't even think I'm going to show a lot of the work on this. Delta H of 4 means that we're going to add together delta H1 plus delta H3 plus the negative of delta H2 that we multiplied by 2. Okay, so here's my delta H1, so negative 1172, and I'm adding that to delta H3, negative 388, and I'm adding that to 114 doubled, but the whole thing, this whole thing that I doubled is also going to be negative, and so that means I get negative 1,788 kilojoules per mole of reaction. And then the last one, the K values. To get K4, instead of adding, we multiply. So we'd do K1 multiplied by K3 multiplied by 1 over K2 squared. So I would take, and my calculator might not like this because it's such big numbers, but 1 times by 10 to the 177th, and I'm going to times that by 1 times by 10 to the 29th. And I'm going to times that by 1 over 3 times by 10 to the negative 13 squared. Okay, so really quick, first thing, let's do this section. So multiply the coefficients. 1 times by 1 would be 1. And then add the powers. So 177 plus 29. So it would be 206. Okay? Now if I take 3 times by 10 to the negative 13, if I square that, then that is 9 times by 10 to the negative 26. And if I do 1 divided by that, that is equal to 1.11, etc., times by 10 to the 25th. So then my final answer, 1 times by 1.11, which would be 1.11, times by 10, and then you add the coefficients there, so that'd be 231, let's see, 206 plus 25, yeah, 31. That's a big number, but that would be our K value. And there's our delta H, and there's our delta G. Alrighty. Now, a couple of things to remember for this guy. Reminder, we have red cat, and also this is going to be our fat cat, right? Because this guy's going to get bigger. And ox, and it eats the ox, so the ox gets smaller. And then don't forget, Leo the lion says grr, so losing electrons is oxidizing, so this guy is going to oxidize, as we know. And then reducing, red cat, gaining electrons, so this is reducing, which means that it's gaining electrons. Now notice something. The electrons are flowing from here to here, so they're leaving this guy and they're entering this guy. So this has to be the cathode because it's reducing, which means gaining electrons. So that's how we can know that this, as it's labeled, is the cathode. And then because this one's losing electrons, this is our anode. Okay. With that cathode, see how silver ions in the solution are being added on to this? It's going to get thicker and bigger and fatter, okay? Where the anode, the opposite's happening. Atoms from the solid are coming off into the liquid, so it's going to get smaller. Now notice that because we're adding cations in here, we need to balance it off with anions. So in the salt bridge, we need the negatives to come over here. Where the opposite is kind of happening. See how we are losing positives? That would make this more negative over here. So we would want some of those negatives to leave or some positives to enter to balance it out. One other reminder. If you replace the salt bridge with wire, the voltage becomes 0. This is wire, this is not wire. And to calculate this voltage, this E cell, or this voltage, we do the cathode minus the anode. And so it's the most positive number minus the most negative number. Okay. Now I'm going to make my way through these problems. Which of the following reaction has the most negative delta S? So most negative means it become more ordered or less chaotic. So I have 2 aqueous turning into 1 liquid and 1 aqueous. That's really similar. I don't think I could say that's a positive or a negative. This is 1 solid turns into 1 solid and 1 gas. That's more chaotic. So that'd be a positive delta S. Here we have 3 gas particles which are just turning into 1 liquid. That's a big reduction. That would be our negative delta S for sure. And then one gas to one gas. So yeah, don't know what's going on as far as delta S goes. So C would be our answer. Which of the following equations represents a reaction for which the standard enthalpy change is a positive? Okay, so a positive delta S means more chaotic or less ordered. So going from 3 crazy gas particles to just 2 would become more ordered. That'd be a negative delta S. Here's 3 gas particles becoming 2 liquids. That's definitely more ordered, less chaotic. That'd be a negative delta S. This guy, though, is 1 solid is turning into 1 solid and 1 gas. So that became more chaotic. And then our last one is 1 gas and 2 solids just turned into 2 solids. That is more ordered. So then C would be our correct answer. Now, calculating delta S, it's products minus reactants. So if I want the delta S for this reaction, I would take the products, which is 2 of these HCl's, products minus reactants. And on the reactant side, we have 1 of these H2s and 1 of the Cl2s, okay? Delta S was 20, and then we are figuring out what the entropy is for HCl. So 2 times by this number, that's our unknown we're trying to figure out. And we're going to minus this from 1 times by H2 and 1 times by Cl2. So this would be 130 plus 220. Okay. Let's see. 130 plus 220 is 350, and it's minus that. So let's add it to the other side. So 350 plus 20, 270 is equal to 2 times by x. So 270 divided by 2 would equal what we're trying to solve here. 135, that's not one of our answers. ABC, but am I missing, like, did one accidentally go away? ABC, I bet there's a D that's supposed to be here, y'all. But double check my math, I could be wrong. 135 joules per mole Kelvin. Okay, I think it would have been that. Now, first thing I'm noticing, negative delta H, this is a good thing. This is like a driver of the reaction. And then we have 1 solid and half of a gas is just turning into 1 solid. So this becomes more ordered because we're losing that gas particle. So that would be a positive delta S. And so the question is it is observed that the reaction producing KCl from its elements goes essentially to completion. Which of the following is a true statement about the thermodynamic favorability? If it's happening, then we know that our delta G is negative. It's thermodynamically favorable. And we see that this guy is our driver. And then, oh, I put a positive. It's supposed to be a negative because it became less chaotic. So remember when I'm telling you in the table where it's like delta H was negative and delta S was negative, and so then it was only thermodynamically favorable at low temperatures. So answer option A says the reaction is favorable and driven by enthalpy. The reaction is unfavorable and driven by entropy. the reaction is favorable and driven by both enthalpy and entropy. The reaction is unfavorable due to both enthalpy and entropy. I'd say that it's driven by enthalpy, and so that means A is the correct answer. The reaction did happen, so it is favorable, and it was driven by our delta H. Now, number 5, when solid ammonium chloride is added to water, it dissolves and the temperature of the solution decreases. So this would mean that we have a positive delta H if it's endothermic, if the temperature decreases. Which of the following is true for the value of delta H and delta S for the dissolving process? It did dissolve, so we have a negative delta G. So delta S had to be positive, because if delta H was positive and this was negative, then there's no way that the delta G could have been negative. So this has to be positive to drive the reaction to occur. So delta H is positive and delta S is positive. For number 6, which of the following is most likely to be true about the reaction between SO2 and O3? Oh, at this temperature. Okay, so see how we have our negative delta H and our negative delta S. So it's kind of the opposite of the one we just did. If delta G is going to be negative, like if this reaction is actually going to happen, and we have negative delta H and negative delta S, then it's only thermodynamically favorable at low temperatures. So let's see what we got here. Delta G is negative, and we want low temperatures. So we want this driver to be our delta H. So we would want this temperature to be low, which would make it smaller in magnitude, where delta H could be bigger and it could be the driver of the reaction. Okay, now if it tells you that a reaction is happening, so it should, if they tell you that the reaction is a negative delta G, so it should be happening, but it's not happening. The reason why is because of the activation energy. Like, the activation energy is just too high for that reaction to occur. So here I see a negative delta G. Like, this reaction should be happening. And it says, even though the reaction represented above by the even though the reaction represented by the equation above is thermodynamically favorable, the formation of the sulfur was not observed. And so, like I was telling you, this only occurs when we're dealing with a large activation energy. Right here. So at 298 Kelvin, the energy of most molecular collisions is lower than the activation energy. The activation energy is too high for the reaction to occur. Now, number 8, we see something similar. Delta G is negative, so the reaction should be happening. However, H2O2 is typically stable for up to a year, stored in the dark bottle, so it doesn't decompose. And so we're going to say, well, why is that? And it's because the activation energy is too high. That's why the reaction is stable. It's not occurring. Now, just a reminder, because we did put this in the table, when we have a negative delta G, that means that our K value is larger than 1. But when we have a positive delta G, that means our K value is in between 0 and 1. So if we add these two reactions together, it gives us, oh wait, we don't want to just add them together, because look, 2 iron oxides, that one's fine. But carbon solid, here's carbon solid, but it's on the product side and it's on the reactant side. So we actually want to flip this reaction. We want to change it so it's carbon solid plus O2 gas turns into CO2 gas. And our K value, we're going to do 1 over this K value. And when we flip it, then the oxygens cancel, and we're left with this overall. Okay, great. If I call this overall reaction 3, K3 would be K1 multiplied by 1 over K2. So like, here's K1, 1 times by 10, here, let me put in parentheses, 1 times by 10 raised to the negative 6. And I'm going to multiply this by 1 divided by the K2, 1 times by 10 raised to the negative 32nd. And that would equal 1 times by 10 to the 26th. So that narrows us down to C or D. Now this is a number that's much bigger than 1, so that must mean that delta G is negative. Similar idea, delta G this time is positive, so that's why K has to be in between 0 and 1. Okay. Which of the above occurs for the following circumstances? The silver electrode is made larger. If one of the electrodes gets bigger or one gets smaller, the voltage doesn't change. No change in voltage. However, if the salt bridge is removed or replaced with a wire, then the voltage becomes 0. Now, reminder, if I'm solving for this E cell, it's the cathode minus the anode. And to get the most positive number, I would want the most positive number for the cathode and minus from the most negative number for the anode. So in this scenario, I would have the silver be the cathode and then minus this from the negative 0.76, and so the zinc will be my anode. And plugging that in my calculator, I believe we get 1.56. That 0.8 minus the negative 0.76. Great. This is our cathode. This is our anode. Now remember though, red cat, we reduce at the cathode. And this is reduction. See how the silver is gaining the electron? But unfortunately, this is also reduction. So we need the anode to oxidize, so we're going to flip that reaction. So the cathode reaction is fine, but we're going to flip the anode. So this is going to be zinc solid turns into zinc 2+ and 2 electrons. Now, for these redox reactions, we need the amount of electrons being gained and lost to be the same. So the last thing I'm going to do is I'm going to multiply this top reaction by 2. So 2 silver, 2 electrons, and 2 silver solid. This means that the electrons will cancel and we'll be left with 2 Ag plus zinc solid results in zinc 2+ and 2 silver solid. And that's why D is our final answer. But I do want to point something out. Even though we flipped this equation, I didn't change the number down here. And just because I doubled the top one, I didn't change the number here. I didn't double it. So just do the most positive minus the most negative when it comes to the voltage. So something similar here. We have our okay, so then see how this is the most positive? So this is going to be our cathode. And this is the most negative, so it's going to be our anode. So if we take the cathode and it's reducing, so we leave it just the way that it is, it's gaining electrons, which is reducing. And then we flip the anode because that needs to oxidize. So we'd get Cr2 plus turns into Cr3 plus and an electron. Now the amount of electrons being gained and lost need to be the same, so I'm going to multiply this bottom reaction all by 2, and that means our overall would be copper 2 plus 2 chromium 2 plus turns into copper solid and 2 chromium 3 plus. Okay, yeah, B. Now we're getting the voltage here, so I'm not worried about if I'm multiplying or I'm flipping. I'm just taking the most positive number minus the most negative number. 0.8, which is B, 1.21 volts. All right, nice. Now we're on to the free response. Okay, I see copper and tin. Reminder, standard galvanic cell. So yes, it is at standard pressures, 1 atmosphere's temperature, 25 degrees Celsius, but the concentrations are also standard, which is 1 molar. Okay. Identify the electrode at which the oxidation is occurring. And let's see. As current flows through the cell, the student determines that the copper electrode increases in mass. Okay. And then the tin electron decreases. Reminder, fat cat, right? So this is our cathode, and reduction happens at the cathode. So gaining electrons, like electrons must be traveling this way, and we're gaining atoms onto there. And then anode and oxidation happens. This makes sense because we're losing electrons. And so identify the electrode at which oxidation is occurring. That would be SN. Explain your reasoning based on the student's observation. So here's the idea. We're going to have this tin solid, this SN solid, and it's going to lose electrons and become SN2+, that's aqueous in the water there. So that's what I would explain. I would explain that this SN solid will turn into SN2+ aqueous as it loses those 2 electrons because it's oxidizing. And that's where this solid is disappearing. That's why this electrode is getting smaller. So I'd give a sentence or two about that. As the mass of the SN electrode decreases, where does the mass go? Into the solution as SN2+ aqueous ions. In the expanded view of the center portion of the salt bridge shown in the diagram to the right, draw and label the particle view of what occurs in the salt bridge. Okay, so remember how the cathode was over here, the anode was over here. So see how we're gaining a bunch of negatives over here? or sorry, gosh, gaining a bunch of positives over here, that means we need negatives to come and balance it out. So like the NO3 minus have to come this way. Now similar, these copper 2 plus, they're what are being gained and added onto here. So we're losing cations, we're losing positives, so we need to add more positives in with the K plus. And so that's what we need to see here, is we need to show these guys headed to the cathode and these guys headed to the anode. A non-standard cell is made by replacing the 1 molar solution of the copper nitrate and the tin nitrate in the standard cell to 0.5 molar solution of copper nitrate and tin nitrate. The volumes of the solutions in the non-standard cells are identical to those in the standard cells. Okay, the volumes are the same. Is the cell potential of the non-standard cell greater than, less than, or equal to the cell potential of the standard cell? Okay, so we have E cell right here is equal to the E cell standard minus RT over NF natural log of Q. Okay. Now, great, but Q is an expression, right? Q is products over reactants, and did we get the reaction yet? Okay, so copper copper 2 plus is gaining the electrons and turning into copper solid. That's happening at the cathode. And then on the other side we have zinc solid, which is becoming zinc 2 plus and losing those electrons. So then when we get the overall, this would be copper 2 plus aqueous plus zinc solid turns into zinc 2 plus aqueous plus the copper solid. So if I were to write a Q expression, it'd be products over reactants, but I wouldn't include solids or liquids, right? So this would be concentration of zinc 2 plus, concentration of copper 2 plus. Okay, and they both started at 1 molar, 1 molar, so this would equal 1. And then we changed it to 0.5, so it would be 0.5 and 0.5. So Q stays the same. It didn't go up and it didn't go down. So then that must mean that the voltage is also the same. This whole thing doesn't change, and this is just equal to 1, just like it was before. So there should be no impact happening on this. Did it tell us what the voltage was before? I guess it doesn't really matter. Okay, so this is some positive number. If we do the natural log of 1, and that's 0, okay. So the natural log of 1 is 0. Anything multiplied by 0 is 0. So minus 0 makes no change. So yeah, the voltage stays the same. So is the cell potential of the non-standard cell greater than, less than, or equal to, equal to. So it's equal to the standard cell, because Q is equal to 1 in both cells. Both the standard and non-standard cells can be used to power an electronic device. Would the non-standard cell power the device for the same time, longer time, or shorter time compared to the standard? Shorter time. Now the reason why is because the concentration is less. That like we went from 1 molar to 0.5 molar. So there's just simply less of it, so it's not going to run as long. And so that's what I would explain. I explain when the concentrations of the ions go down, then the reaction ends more quickly because the ions are consumed in that reaction. And so, yeah, that, or explaining how when the ions have a lower concentration, then the battery doesn't run as long, and I think that would work as well. Okay, where are we at time-wise? Okay. I'm going to do what I can, but I don't want to have to do 2 videos, so once this hits the hour mark, then I think I have to be done with the video. Using the information from the table above, write a net ionic equation for a reaction between the SN electrode and the copper nitrate solution that would be thermodynamically favorable. Okay, so reminder that we saw oh, that's so funny that I wrote zinc instead of SN, sorry, SN instead of ZN. Do you see how this SnNO3, that means that this tin was a 2+ because we know our nitrate was a 1-. And so it's trying to be really tricky because we see this 4+ and that we're not using that guy. We're using this one because it's a 2+. And then similar with the copper, same deal when you go back to that original. So we're using this guy, we're not using that one. So now, what do they want? Let's see. Write the net ionic. Okay, so we decided that the copper was the cathode, right? Oh, guess what? We did this. If you just take this and put that, oops, I guess it's onto the next page. Next page. If you just put that right here, that's our answer. Okay. Calculate the value of delta G for the reaction. Now, one way to do this is with the delta E, or sorry, the E value, where we take the most positive, so that 0.34, and we minus it from the most negative. So our voltage would be 0.48 volts. And then we can take N, which is the moles of the electrons, and then F, which is Faraday's constant right there. So delta G is equal to negative NFE standard. So delta G is equal to negative. Now, reminder, it was 2 moles of electrons, right? 2 gained and 2 lost. So then it'd be 2 moles of electrons. I'm going to multiply that by 96,485 coulombs per mole of electrons. Right there. And then that's going to be times by 0.48 volts. So -2 times by 96,485 times by 0.48. So it looks like delta G is going to be -92625.6 joules. Okay. I think I'm going with 2 sig figs. This is exactly 2. So kilojoules is helpful. We don't have to, but we could do. That'd be negative 92.6 or negative 93 kilojoules per mole of reaction. So that would be a good unit for us. Okay, write the net ionic. So I'm going to take the most positive guy, and let's do this first because I just think it's more helpful. So the E cell is our cathode minus our anode. So the most positive value, 0.34, minus our most negative, 0.76. 0.34 plus 0.76. That means our voltage is 1.1 volts. And this tells me that this is our cathode, so copper 2 plus 2 electrons equals copper solid. I'm going to leave that the way it is because that's reducing, gaining electrons, and we reduce at the cathode. But I'm going to flip the other one. Oh, it's the same. It's like the same problem. So zinc solid. Yeah, this is literally the same problem. Okay. They have a different value here, but that doesn't really matter. Zinc 2 plus and 2 electrons. Because the electrons gained and lost are the same, I don't need to multiply anything. So we'd have copper 2 plus aqueous plus zinc solid turns into copper solid and zinc 2 plus aqueous. Okay, let's keep going because this is very similar to the last one that we did. Okay, the following diagram on the left represents the copper nitrate solution in the half cell before the galvanic cell starts to operate. In the following diagram on the right, draw a representation of the solution in the same half cell after the galvanic cell has operated for some time and is still producing voltage. Okay, so gaining electrons, so the electrons are flowing this way. And then these little copper 2 pluses that are hanging out here, they're going to add onto those electrons and become copper solid. So because we're losing positives, we're going to gain more positives with that potassium coming in there. Okay? So what we're going to want to see is these copper 2 pluses. I would leave at least one of them because it says the reaction's still happening. But the other ones, let's replace them with potassiums. And then there was 1, 2, 3, 4, 5, 6, 7, 8 of those nitrates. So I would do probably the same amount of nitrates in there. For the standard cell, the copper 2 plus half cell is made with 1 liter of 1 molar copper nitrate, and then 1 liter of 1 molar. This is, guys, this is such a similar problem to the last one. So let's move on to the very last free response, which is 19. Okay. See how the electrons are flowing this way? So this must be my cathode, and this must be my anode. Because we're gaining electrons, which is reducing, and then losing electrons, which is oxidizing. Now, notice how the zinc goes from a 0 to a +2. That's losing electrons. So this must be our zinc because it's oxidizing, where the nickel 2 plus becomes nickel solid, so this is a +2 that becomes a 0. So that gained electrons. So that's reducing. So identify M and M2 plus. Okay, so now we know M is zinc. This is That's what M was. And that our M2+ must be zinc 2+. And specify the initial concentrations. Now, it said that it was a standard half cell, so that would be standard temperatures, which is 25 degrees Celsius, pressures, which is 1 atmosphere, and standard concentration, which is 1 molarity. Indicate which of the metal electrodes is the cathode. Write the balance equation for the reaction that occurs in the half cell containing the cathode. So indicate which of the metal electrodes is the cathode. So the cathode is the nickel, okay? And then the half reaction is the nickel 2+ is gaining 2 electrons, and then it's becoming nickel solid. I'd put aqueous with that as well. So there's, right, the balanced equation for the reaction that occurs in the half cell. Yeah, that's it. What would be an effect on the cell voltage if the concentration of zinc was reduced to 0.1 in the half cell containing the zinc electrode? Okay, so reminder that the equation is zinc solid plus nickel 2+ aqueous turns into nickel solid and zinc 2+ aqueous. So if I were to write a Q expression for this, it would be my zinc 2+ over my nickel 2+. Okay. Now, it started off where both of these were 1 molar and 1 molar, but now the zinc is reduced, that this is 0.1, and then this didn't say anything about changing, so this is probably 1. We saw right here that Q will influence this voltage of this new cell. And if we think about this for a second, so we have 0.1 divided by 1, which would be 0.1. Now, the natural log of 0.1, this is a negative number, right? So this is a negative number, but if we minus a negative, that makes it positive. So E cell plus something would make this guy bigger. So would the effect on the voltage if the concentration of zinc was reduced in the half cell container? The voltage would increase. What would be the effect of the cell voltage if the concentration? Yeah, look, it doesn't say explain or justify, but yeah. So it's looking like if Q becomes smaller, then the voltage gets bigger. So remembering that relationship, I think, will be helpful. Describe what would happen to the cell voltage if the salt bridge was removed. Anytime we remove the salt bridge or we replace the salt bridge with a wire, it stops the movement of electrons, and the voltage becomes 0. So describe what would happen to the cell voltage if the salt bridge was removed. The voltage would become 0. And then your explanation could be as simple as the reaction stops occurring, so the electrons stop moving. That would totally work. Okay, we just squeaked it in this video. So there is our Unit 9.